Hi everyone, welcome back to my YouTube videos. In this video, I'm going to continue with the analysis of bond percolation in 2 dimensions. So I remind you that for bond percolation in any dimension, in fact, the process exhibits a phase transition at some critical value PC. Looking at those pictures, you have on the left what the process looks like in the subcritical phase, and on the right what it looks like in the supercritical phase. So on the left, when P is strictly less than PC, you see that all the clusters are finite. We know that all the clusters of open edges must be finite, and we saw that in fact clusters are typically small. You have an exponential decay in the cluster size. At the opposite, if you look at the picture on the right, you see a unique giant component that covers most of the space. And in fact, the main result in this case is the existence and uniqueness of something that we call the infinite percolation cluster. So meaning that in the supercritical phase, there exists a unique infinite cluster of open edges. Now, you see clearly that in those two pictures we are in the two different regimes, so that means that most likely the phase transition should occur between those two values, 0.45 and 0.55. In fact, it turns out that the critical value for bond percolation in 2 dimensions is exactly equal to 1/2, and that's what we are going to prove in this video. So this result is due to mathematician Harry Kesten, and before we start with the proof, I want to remind you 2 important properties we saw before. That's going to be 2 important ingredients to prove the theorem. The first one is existence and uniqueness of the infinite percolation cluster. So the existence part is not the most important. The most important is more the uniqueness part of the result. So let's have in mind, let's keep in mind that there cannot be 2 infinite clusters of open edges in the supercritical case. And the second ingredient is something we defined in the previous video, that's planar graph, this idea of planar graph and planar duality. So I quickly remind you that in the previous video, we saw that the 2-dimensional lattice, that's basically where bond percolation in 2 dimensions is taking place. So this infinite graph is self-dual. That means that the dual of this graph is isomorphic to this graph itself. And from that, we were able to construct a coupling of 2 bond percolation processes that are characterized by a few important properties that also we need to keep in mind. So first, those 2 bond percolation processes have the same parameter, but are not defined on the same graph. What I'm going to call Xi is bond percolation defined on the original 2-dimensional lattice, while the other process Xi hat is defined on the dual of the 2-dimensional lattice. So we have 2 different bond percolation processes defined on 2 different graphs that are isomorphic, but the 2 processes still have the same parameter P. Also, another important property to keep in mind is that the coupling is such that open paths in one process cannot intersect closed paths in the other process. So now let's prove that indeed the critical value of bond percolation in 2 dimensions is equal to 1/2. I'm going to divide the proof in 2 steps. First, we are going to prove that PC is less or equal to 1/2, and then we are going to prove in fact something slightly stronger than the fact that PC is larger or equal to 1/2. And I'm going to explain when we go to the proof of this step why in fact the result is stronger. So first, let's prove this result. First step, most of the proof is based on some kind of very elegant construction, so I'm going to explain this construction. So first, we are going to take a subgraph of the 2-dimensional lattice that looks like this. So that's going to be in fact a sequence, a growing sequence of graphs. So we take 4 by 3 vertices like that, and we connect them like this. So all those vertices are in fact in Z2. So what I'm drawing here is a subgraph of Z2 of the two-dimensional lattice, and then in red I'm going to draw some kind of dual of that by looking at vertices here. And then the way we are going to connect them is like that, so similar way, like this, and then we go here, and like this. So we have two subgraphs like that. I'm going to call the black one Gn. So the reason why I'm putting an n here is that in fact we have a sequence of subgraph. Here the picture I drew is a picture of G3 because we have 1, 2, 3 vertices here, and the right graph I'm going to call it Hn, but the picture is a picture of H3 because we have again 3 vertices. So now what's important in this picture is to notice that in fact those two graphs are completely are in fact the same from a topological point of view. They are isomorphic, and in fact you can just rotate one of them to obtain the other one. So that's some very important thing we have to keep in mind for the proof. From those two graphs, ultimately have in mind that their size depend on n. So in fact, that's increasing sequence of subgraphs, and in the proof we are going to take the limit when n goes to infinity. So now I'm going to define two events based on realization of bond percolation. So those two processes xi and xi hat that are attached to those two graphs. So the first event an says that there is an open path on Gn for the process xi going from left boundary to right boundary. Okay, so I'm going to write here that's the event that there exists an open path in the process xi, let's say going from the left to the right boundary. I'm just going to write that on the graph Gn. Okay, so of course, because the event is attached to some event on the subgraph Gn that also depends on n, that's why I put some n here. And I'm going to define another event Bn that is similar, but I'm going to do a few modifications, but that's going to be kind of like completely symmetric. I'm going to replace xi by xi hat. We look at the over marginal in the coupling of the two bond percolation processes. Instead of looking at something happening on Gn, we look at something happening on Hn. And instead of having a path going from left to right, we go from top to bottom. I'm also going to change the definition by saying that instead of an open path, we want a closed path. So eventually we have that Bn is the event that there exists a closed path, but this time it's in xi hat, going from top to bottom, so like this, on the subgraph Hn. Okay, so we have those two events. Now, because it turns out that in the proof we are going to take the limit when n goes to infinity, so this picture here is not very interesting for us. After, I'm going to draw some kind of macroscopic version of that without drawing all the edges, but the graph, in fact, they should look like this. So the first graph, Gn, that I'm going to draw in black, I'm going to represent that by just a box like that. And the other graph, Hn, is something like this. Okay? And now, what about those two events? Now I'm going to draw pictures of those two events. So in black, I'm going to draw the event An. So An means, again, that you can find a path going from left to right, so something that looks like that. And Bn is the event that you can find. You have a closed path going from top to bottom, so that looks like this, let's say. So now if you look at the picture, that tells you that you have an open path in xi here, that must intersect a closed path in Xi hat. So you see that those two graphs, Gn and Hn, indeed they are built in such a way that if you go from top to bottom of Hn, then you have to cross anything that goes from left to right of Gn. And so from that we deduce that in fact this feature is not possible. And so why is that? Well, because the way we define the coupling between those two processes is in such a way that open path in Xi cannot intersect closed path in Xi hat. So that means that this feature is impossible, which also means that those two events in fact are mutually exclusive. So I'm going to write that. So first thing we can say is that an intersection Bn is equal to the empty set. Now, second properly we can say about those two events is that if now at the opposite you cannot find, let's say, any path going from left to right, then that means that none of the paths starting from here can reach the other side. And so that means that eventually you can find a sequence here of closed edges that you can cross to go from top to bottom, okay? And so you can have this event. So what I'm trying to explain here is the fact that in case an does not occur, you cannot connect the left and the right, then you can find in fact gaps in the middle, and you can follow those gaps and have a closed path going from top to bottom here. So if an does not occur, then Bn should occur, and similarly, if Bn does not occur, then an must occur. So that means that the union of those two is equal to the set of all the realizations. So we have an union Bn is equal to, well, the set that we usually call omega. So those two things mean exactly that an and Bn form a partition of the set omega. And so from this, so let's keep that in mind. Maybe I can, let's keep that in mind, that's fine. So we kind of have features here. So from the fact that an and Bn form a partition of omega, we deduce that P of an plus P of Bn should be equal to 1. Okay, and here I'm going to precise, to put a little p to recall that edges in both cases for those two events are open with probability p. Now, other thing we can say is the fact that it's to look at p of probability, but this time the parameter is going to be 1 minus p of an. So what can we say about this probability? So now we are looking at the probability that we can indeed go from left to right using an open path. But now we assume that edges are open with probability 1 minus p. So now it turns out that if edges are open with probability 1 minus p, this also means that they are closed with probability p. And so that means that the probability that we can go from left to right, that we have a path going from left to right, so the event an, but when edges are open with probability 1 minus p, is exactly the same as the probability that we have a closed path going from top to bottom, but now when the parameter is p. So what I'm saying here is something like if we replace p by 1 minus p, it's kind of, at least from a stochastic point of view, the same as saying that, well, closed edges, if you replace all the closed edges by open edges and all the open edges by closed edges, it's exactly like redefining another realization of bond percolation, but where now the parameter is going to be p, 1 minus p instead of p. And this means that the probability that we can go from left to right if the parameter is 1 minus p is exactly the same as probability of Bn, but now when the probability of having open edges is equal to p. Okay, and so we have that this is equal to the probability of Bn, but now the parameter is p. Okay, so now using those two things, we can prove this inequality here. So first, to prove that we are going to start by taking a p strictly less than pc and see what's going on. So we start from p strictly less than pc, and using those two equations here, we can deduce another inequality between p and pc, and that's going to give us this inequality here. So p less than pc means that we are in the subcritical case, and so if we are in the subcritical case, that means that p of n, when n is large, should go to 0. Okay, p less than pc means that there is no infinite path, or the path should be small, and so that means that the probability of connecting left and right boundaries should go to 0 as n goes to infinity. At the opposite, if p was larger than pc, we would have something the other way around, that the probability of n should go to 1. But here we are in the subcritical regime, so that implies that the limit when n goes to infinity of p of an, and I'm going to precise p sub p of an again, it's probability of a long open path. If p is less than pc, the probability of this long open path should be 0, so in the limit that's 0. So then, going back here, we know that because the sum of the two here is equal to 1, that means also that this limit here implies that the limit of p sub p of bn should be equal to 1. So this implies that limit when n goes to infinity of p sub p of bn is equal to 1. Now, next step, I'm going to use the fact that those two probabilities are equal, so that means also that the limit when n goes to infinity of this probability is equal to 1. So implies that limit when n goes to infinity of p 1 minus p of an is equal to 1. And then from that, you see that it's exactly the opposite as here. So if indeed n is very, very large, and you can connect left and right, that means that this parameter, and so now this 1 minus p is the density of open edges, should be larger than, so that means that, let me see, so this one, 1 minus p should be larger or equal to pc, so from that we deduce that 1 minus p should be larger or equal to pc. So indeed, to be able to connect left and right if n is very large, so the graph here is very large, that's only, so the only way that this limit is 1 is if this density of open edges is larger than pc. We are here in the supercritical regime. So conclusion, what we prove is that if p is less than pc, I'm going to erase that now. So if p is less than pc, then this implies that 1 minus p should be larger than pc, which also implies that I'm going to rewrite this using p again. So this implies that p here should be less than 1 minus, let me see. So p should be less or equal than 1 minus pc. Okay? And so from that you deduce that, so if p is less than pc, then it should also be less than 1 minus PC, and so from that you deduce that, I should write, so that's not, this implies that this whole thing, this implication implies that PC should be less or equal to 1 minus PC, and so you get 2PC less than 2, which indeed implies that PC is less or equal to 1/2. So that shows indeed the first part of the theorem. So now let's prove at the opposite that PC is larger or equal to 1/2. So of course with what we just proved, that's going to imply that PC is equal to 1/2. And in fact, you see in step 2 in the slide, we are going to prove slightly more. We are going to prove the fact that theta of 1/2 is equal to 0. So I wrote this result on the board. So the main point is not to prove this implication. The main point is really to prove this result here, that theta of 1/2 is equal to 0. So why this implies that? Well, because theta 1/2 equals 0 means that if the density of open edges is equal to 1/2, then there is no percolation, so we are kind of subcritical, and so that means that indeed to have percolation we need to take P strictly larger than 1/2 here, and so indeed that shows that PC must be larger or equal to 1/2. Now you see also that this is, so why is it stronger than saying that just PC is equal to 1/2? Well, PC equals 1/2 would tell us that if the density of open edges is strictly less than 1/2, we don't have percolation. If the density of open edges is strictly larger than 1/2, then we have percolation. But the fact that PC equals 1/2 doesn't tell us anything about what happens at the critical value PC. And so this result is stronger because it also says that 1/2 is like subcritical. So it's like the behavior of bond percolation at its critical value is similar to the subcritical bond percolation process. So that's in the sense that it's stronger. So now, how can we prove this result? Well, the beginning of the proof is exactly the same as for the first step, in the sense that we are again going to use those two graphs, Gn and Hn, and define events from that. So I'm going to redraw a picture, and a picture of those two graphs. So we said that Hn looks, Gn looks like that. That's a subgraph of the two-dimensional lattice with n plus 1 by n sides, vertices. Hn is something that looks like this. That's a subgraph, now this time with n by n plus 1 vertices, and that's going to be a subgraph of the dual. So now we are again going to define two events from that. So in the step 1 of the proof, we had path open or closed, like going from left to right or top to bottom. Now what we are going to do instead is look at path, infinite path starting from the left boundary and the right boundary, but not crossing necessarily those squares. So what I'm going to write is, so first event is going to be again something of the form an. I'm going to call it an prime because that's not the same as before. So this one says that there exists, let's say, infinite open path in fork C, okay, starting from so left and right boundary, left and right boundaries, so of Gn, okay, and the other events we are going to define, Dn, again that depends on n, that depends on the size of the graph. Again, so same story as before, we replace left, right by top, bottom, we replace Gn by Hn, we replace C by C hat, so we have exactly the same thing, except that playing with those parameters P1 minus P, instead of assuming that we have open path, we are going to assume that we have closed path. So this is the event that there exists, again, infinite, but this time closed path. Now those paths are in Xi hat, and now they are starting from we said top and bottom. Okay, of Hn. Okay, so we define those two events, and then, so maybe let me draw a picture of that. So An means that, you know, starting from somewhere here, you have some infinite path, and starting from somewhere here, you have another infinite path. And Bn means that you have the same but with closed path. So you go there, and this one, I don't know, goes forever like this. Okay, so these are pictures of those events An prime and Bn prime. So maybe to save space, I'm just going to keep the picture, and I'm going to draw, like, write the event here. So we have An prime here, that's just a picture of An prime. Remember that just this event is dealing with open path, while Bn prime is dealing in red, like with a closed path. So here we have that, and here we have a picture of Bn prime. Okay, so that's those two events. I'm going to erase this now. So again, I've also in mind that this path just keeps on going, goes to infinity. So let's make it go there. And okay, so these are those two events. So you see that they don't necessarily cross those graphs here. They just start from the left and right boundaries, or bottom and top boundaries, and they are infinite. So now, to prove this result, so now we know the implication, so maybe I can just erase that, okay? The implication is known. What we want to prove is this. I'm going to assume by contradiction that this is not true, so that means that theta of 1/2 is strictly positive. So assume by contradiction that theta of 1/2 is strictly larger than 0. So that means that for p equals 1/2, there is percolation of the process. So in this case, let's look at those events. So that means that if p is equal to 1/2, okay, because we have percolation, then An prime should occur with probability close to 1 when n is large. Because I'm going to increase this box, so I have more and more and more vertices, like those two boundaries are going to get bigger and bigger, and so they are going to cross somewhere the infinite percolation cluster, okay? So eventually, we can deduce from that if p equals 1/2, the probability of An prime is going to go to 1. Now, it turns out that if p is equal to 1/2, density of open edges is equal to 1/2. That also means that the density of closed edges is equal to 1/2. And then, by perfect symmetry, you can say that, well, that means also that the probability of Bn prime should go to 1 when n goes to infinity, okay? Because you can exchange like open and closed edges, you don't really change the parameter. When p is equal to 1/2, 1 minus p is also equal to 1/2. Density of open edges is equal to density of closed edges. So that means that if for p equals 1/2 you have percolation for the black process, then you should also have percolation but looking only at the closed cluster of closed edges for this process, for the red process. So this implies that if this is true, this implies that the probability of An prime and Bn prime are both equal to 1, or sorry, I should write instead, I forgot to take the limit. So this implies that the limit when n goes to infinity of the probability of an prime intersection bn prime should be equal to 1 when the parameter is 1/2. Okay? Again, the reasoning is that, well, those two events, in fact, the only difference in the probabilities of those two events is that this one is dealing with open path, this one is dealing with closed path. And so that means that, again, the probability of an prime with parameter p should be the same as the probability of bn prime with parameter 1 minus p, but when p is equal to 1/2, p and 1 minus p are the same. So we indeed have this. And so that means that we have indeed those two events, it's, with probability close to 1, those two events are going to occur at the same time. So which means that this picture is possible. Okay, in the first step of the proof, you remember, I drew a picture that was impossible, but if we have that, that means that this picture is possible. Now, it turns out that and that's now that we are going to use existence and, most importantly, uniqueness of the infinite percolation cluster. So, because of uniqueness of the infinite percolation cluster, if you have an infinite black path here, that means that this black path has to be part of the infinite percolation cluster, because there is only one. So that means that this path is basically embedded in the infinite percolation cluster. Same story for this one, but so that means that those two infinite paths, they cannot be disconnected. They are both subsets of the same cluster, and so they must be connected somehow, okay? So that means that there is a vertex here and another vertex here, and there must be a path of open edges connecting those two ones, okay? So maybe let me draw this. So maybe that looks like that. But then, same reasoning for bn prime, okay? Here we have an infinite path of closed edges. Now here again an infinite path of closed edges. Same story, if you replace closed by open, that's kind of the same idea. You must have, because you have uniqueness of the infinite percolation cluster, that means that this path and this path, in fact, are subset of the same cluster, of the same infinite cluster of this time closed edges, so they must be connected. So that means that there is a vertex somewhere here and another vertex there, and those two vertices must be connected by a closed path. So now look at the picture. Is it possible to connect those two vertices by a red line, by a red curve, without crossing the black curve? No, that's not possible. You see that the choice of the left and the right boundary makes so that basically you have some kind of, and they go to infinity, so implies that there is no way around this infinite path. This black path here that goes from infinity and follows here and keeps going there is really going to cut the whole space into two pieces, into two infinite half space, and this path is on one half, this path is on the other half. So the only way to connect them is to cross the black path somewhere. So that means that we must have something like this. And then here we end up again with an intersection between a black open path and a red closed path. Again, by construction of our coupling sig c hat, we said that's not possible. So that means that, well, conclusion, we have some contradiction, okay? This assumption here, which implies that the limit here should be equal to 1, leads to a contradiction that we see in the picture. So that implies, let's say, contradiction. And so, which means that our assumption here at the beginning was false, and conclusion, indeed, theta of 1/2 is equal to 0. And so in fact, we have this conclusion. And so indeed, that completes the proof of the theorem.